So what we've observed so far about Riemann sums is that they approximate areas above the x-axis as positive values and areas below the x-axis as negative values. We've also observed that the total area is a net value, and therefore it can be positive, negative, or zero. But now for the big question. We've been using Riemann sums to approximate the area between a curve and the x-axis. And approximations are good. But is there a way for us to make these approximations exact? And the answer to that is yes. And it involves a limit. And this is the formula for net area. And when I say net area now, I no longer mean an approximation, but I mean the exact net area between a curve and the x-axis. So let's break this formula down piece by piece so that we can see exactly what's going on here. Well, let's start with the most familiar piece. That's the piece you see highlighted here in yellow. This portion of the formula should look familiar to you because this portion of the formula is just the height of a rectangle multiplied by delta x, the width of the rectangle. So this portion of the formula represents the area of a rectangle. Now let's look at the part highlighted in blue. This part of the formula probably does not look familiar. The big figure that you see there is the Greek letter sigma, and sigma literally means sum or summation. So that means that we're going to be summing the areas of rectangles. Now the portion below the sigma, k equals 1. In this case, 1 is what we call the lower limit of the index. And this variable k is just a dummy variable. Because as you can see, k will be plugged into our function. We'll have f of x sub k. So when k equals 1, we'll plug that in to f of x sub k, and we'll have f of x sub 1. That will give us the height of our first rectangle. When k is equal to 2, we'll have f of x sub 2, and that'll be the height of our second rectangle. And we'll keep plugging in successive k's to find the height of successive rectangles. And we'll do that until we reach our upper limit of our index, the n above the sigma notation here. So if n is 4, we'll find the heights of 4 rectangles. If n is 10, we'll have the heights of 10 rectangles, and so on. So here's what we have so far in our formula. We have the sum of the areas of n number of rectangles. But here's the kicker, the part in green. Now we're going to apply the limit of that entire expression as n approaches infinity. So what is that saying? That's saying that the number of rectangles is approaching infinity. And as we saw in a previous video, as the number of rectangles approaches infinity, our net area value gets closer and closer and closer and closer to the actual area under a curve. As a matter of fact, it becomes so close to the actual area under a curve that it is indistinguishable from the actual area under a curve. Now there's something to keep in mind here as we take the limit of this sum. If the number of rectangles is approaching infinity, that also means that delta x, the width of each rectangle, must be approaching 0. So sometimes you'll see this formula written as the limit as n approaches infinity, or as the number of rectangles approaches infinity. But if the number of rectangles is approaching infinity, that means that the width of each one of those rectangles has to be approaching 0. So sometimes you'll see this formula written as the limit as delta x approaches 0. The limit as delta x approaches 0 and the limit as n approaches infinity are the same thing. But that's a big messy formula, and you know mathematicians, well, sometimes don't do big and messy. We have to make shorthand for everything. So what you see here is shorthand for what we call the definite integral. The sigma that you see on the left is equivalent to the elongated s that you see on the right. Both of these mean sum. And you may be thinking to yourself, well, I've already seen this elongated s figure over here on the right, and it meant antiderivative. And you're right. That symbol does mean antiderivative, and it also means sum. And we'll talk about why that is in a future video. We'll connect those two concepts together. The a here is what we call the lower limit of integration, and the b is the upper limit of integration. And these two values are the x values between which we're finding the area under the curve. So if we wanted to find the area under a curve for a given function between x equals 2 and x equals 5, a would be 2, that's our lower x value, and b would be 5, that's our upper x value. So when we put these two pieces of the definite integral together, they mean find the net area between x equals a and x equals b. Well, what area? We want to find the area under a curve. And that curve is defined by the function f of x. And we call this f of x the integrand. And then dx is the differential. And technically that dx stands for the width of each one of our infinitely many rectangles. So there we have it. That entire expression, the elongated s with the a at the bottom, the b at the top, and then the f of x dx. That's what we call the definite integral. And that definite integral is a limit of the sums of the area of infinitely many rectangles. And that definite integral will get us the exact value for the area under a curve.